Today's topic will be mole and molar masses. The objective that will be covered in this topic are 1. To define the mole and molar mass, and 2. To perform calculations involving molar masses given atomic masses. Let us begin. The mole is normally a very challenging topic for students, so I'm going to try my best to make sure that it is broken down in a way that you can understand. So let us see, how did the mole come about? Let's talk about some numbers. Now, the mole is used for convenience. Let us look at this example of a number that is convenient. So, which is more convenient to use? If you went to buy eggs, would you want to ask for 144 eggs, or you would ask for 12 dozen eggs? Which number is more convenient to you, 144 or 12 dozen? Well, I'm sure that if you look at these two numbers, you would agree that 12 dozen would be more convenient to use than saying 144 eggs. It would be easier for the person selling the eggs to count out that number of eggs in a container ready to be sold. Now, remember that 1 dozen represents 12. So the conversion factor that we would use here is saying that 1 dozen is equal to 12. So if you went to buy eggs, instead of asking for a large number, you would simply ask for that amount of eggs in terms of dozen that you would need. Another simple example could be looking at pairs of socks. So 2 socks represent 1 pair. And so 1 pair is more convenient than saying 2 socks. So when we look at that, we will see that a mole is simply a very convenient number that represents a very large number. Look at this number right here. 60230000000, so many zeros that the best way to write it is in a standard form. Now, remember that standard form is a very simple way to write a large number. So instead of calling this number all the time, we simply say 1 mole. So a mole is just a convenient number used to represent a very large number. So 1 mole is equal to 6.023 times 10 to the 23rd. Everything that contains 1 mole will contain this number. Now the number can be in terms of particles, atoms, molecules, electrons, or ions. But we must ask ourselves this question: where did this number come from? The 6.023 times 10 to the 23rd. It's a specific number. Where did we get it from? Let us examine the origin of this number. Now, the number originates from scientists carrying out various studies. Now, the scientists counted this number of particles and found that this amount of particles was found in 12 grams of carbon-12. Now, 12 grams of carbon-12 is the mass of carbon-12 isotope, and that isotope is the most abundant element. So every carbon-12, the mass of 12 grams would contain 6.023 times 10 to the 23rd. Now, a comparison of carbon-12 is very important to make that comparison with other elements. So, any element that contains the same number of particles that is in 12 grams of carbon-12, then that element would contain a mole. So we're saying then that any substance containing the same number of particles as there are in 12 grams of carbon-12 would contain a mole. And so comparing all other elements to carbon-12, we use that comparison to find the amount of moles in other elements. If the particles contain 6.023 times 10 to the 23rd, then 1 mole of substance is present. If it contains twice that number of particles, then 2 moles would be present. So notice we keep saying the amount of substance. So amount of substance is another name that we use for the mole. So here we have amount of substance, which is the same thing as the mole. So from this, we will derive a definition. So what is the mole? Well, the mole is the amount of substance that contains as many particles as there are in 12 grams of carbon-12. What are the important terms here? The amount of substance in another element or molecule or ion and so on that contain the same number of particles that is in 12 grams of carbon-12. So all we're doing here is comparing a substance A with carbon-12 isotope. So if this substance A contain this number of particles that is in 12 grams of carbon-12, then this substance contain 1 mole. If it contains twice the number of particles, then substance A contains 2 moles, and so on. So any substance that contains 6.023 times 10 to the 23rd amount of particles would have the same amount that is in 12 grams of carbon-12. Now remember that we can change particles to molecules, electrons, ions, and so on. So instead of saying the number of particles, I could say the number of molecules, the number of ions, the number of electrons, and so on. Let's look at a very important term that will be used in relationship to the mole. That term is the molar mass. Now, what is the molar mass? Well, the molar mass is the mass of 1 mole of a substance expressed in grams per mole. So, the unit of the molar mass is grams per mole, and it is the mass of 1 mole of a substance. How do we know that the substance is 1 mole? Well, we know the substance is 1 mole if it contains this number of particles, 6.023 times 10 to the 23rd. Now, this number is called Avogadro's number. Avogadro is the name of the person who found out that any substance that contains this amount of particles would have the same amount of particles as in 12 grams of carbon-12. And so, you will be hearing about Avogadro's number as we go through the mole concept. Now that we know the definition of the mole and we know the definition of the molar mass, what are we going to do with it? Or what can we do with it? Let's see. Well, we can use the mole and the molar mass to carry out various calculations. Example, calculating mass to moles, moles to mass, as well as calculating percentage compositions by mass. Now, in doing our calculation, our units are going to be very important. So let's understand what are some of the units. The unit of the moles is mole, M-O-L. The unit of mass is grams. And the unit of molar mass is grams per mole. So if you're doing any calculation and you get kilograms, then it would be wise to convert kilograms to grams. Here is a formula that we will use to work out mass to moles and moles to mass. We will then use a different formula in calculating percentage composition by mass. Now that we understand the mole and we know the definition of the molar mass, let us look at what is the molar mass in terms of its calculation. So what is the molar mass of a particular atom? What is the molar mass of molecules? And what is the molar mass of a certain compound? So I could start by saying, what would be the molar mass of magnesium? Or what is the molar mass of ammonia? Or what is the molar mass of sodium chloride? So you see here, this is an atom, this is a molecule, and this is a compound or formula unit. Now, instead of asking, what is the molar mass? I could separate these into 3 different categories. I could ask for the atomic mass or the relative atomic mass. For this one, ammonia, I could ask for the relative molecular mass. And for sodium chloride, I could ask for the relative formula unit mass. So, the relative atomic mass is the mass of an atom compared to the mass of 12 grams of carbon-12. The relative molecular mass is the mass of a molecule compared to the mass of 12 grams of carbon-12. And the relative formula mass is the mass of an ionic compound compared to the mass of 12 grams of carbon-12 isotope. So these 3 terms, relative atomic mass, RAM, for an atom, magnesium, relative molecular mass in terms of a molecule, or relative formula mass in terms of an ionic compound, I could replace all of these 3 terms with one term, which is molar mass. So instead of saying, what is the relative atomic mass of magnesium, I could say, what is the molar mass of magnesium? Instead of saying, what is the relative molecular mass of ammonia, I could say, what is the molar mass of ammonia? And instead of saying, what is the relative formula mass of sodium chloride, I could simply say, what is the molar mass of sodium chloride? So molar mass is used to replace all these separate terms. So note that the molar mass of an element is the mass number. And where do we get the mass number from? Well, if you check your periodic table, you will see that each element comes with a particular mass number. Now, the mass number is made up of protons and neutrons. Let's see how we can work out the mass number of a particular element. Lithium would have a mass number of 7. That is 4 neutrons and 3 protons. Now, you'll notice that the number of protons is equal to the number of electrons in a neutral atom. So let us build the atom lithium. The mass number of lithium is 7. What does that mean? It means that I am going to have 4 neutrons, 3 protons, and of course 3 electrons to make my atom neutral. So this is a lithium atom. To find the mass of lithium, we must know the number of protons and neutrons present in the nucleus. So from this, I can tell that the mass number is 7 because I have 4 neutrons and 3 protons. And my atom is neutral because the number of electrons is equal to the number of protons. Let's use this in calculating our mass numbers in a molecule or a compound. Now, in doing that calculation, it is very important to understand that a mole of a substance contains Avogadro's number. But that is not the definition of the mole. So do not give Avogadro's number as the definition of a mole. Remember that the mole is the amount of substance that contains the same number of particles as they are in 12 grams of carbon-12. And 12 grams of carbon-12 contains 6.023 times 10 to the 23rd. Now, if we want to find the mass number of sodium, you would go to the periodic table and you would look at the mass number. So 1 mole of sodium has a mass of 23 grams. And 1 mole of that sodium would contain Avogadro's number. Now remember we said that the molar mass is the mass of 1 mole of a substance. Hence, the unit is grams per mole. That is simply saying that for sodium, we have 23 grams per mole of sodium. And so the molar mass of sodium is 23 grams per mole, which is the mass number. The same thing would go for magnesium, 24 grams, and that 24 grams would contain 6.023 times 10 to the 23rd, which makes it 1 mole of magnesium. Same thing for aluminum, and so on. So this was used to calculate the molar mass of atoms, which is the mass numbers. Let's look at calculating the molar masses of molecules. Again, 1 mole of a molecule will contain Avogadro's number. And so, if we know the molecule, in this case, the molecule is carbon monoxide, then 1 mole of carbon monoxide would contain 6.023 times 10 to the 23rd molecules. Now, from this formula, we can calculate the molar mass, which is the mass of 1 mole of a substance. So, 1 mole of carbon monoxide, we are going to use the mass numbers to calculate the molar masses. So, you will see that in the periodic table, you'll see carbon having a mass number of 12, and you'll see oxygen having a mass number of 16. In adding these mass numbers, 12 for carbon, 16 for oxygen, you would get a mass of 28 grams per mole. Moving on to water. 1 mole of water is the molar mass of each element summed up. So 1 mole of water would contain Avogadro's number. Now, if you add up the mass numbers for H, the mass number would be 1. For oxygen, it is 16. But remember that water is H2O, so we have 2 hydrogen atoms. Hence, it is 2 times 1 plus 16. So the molar mass of water is 18 grams per mole. In moving on to ammonia, the same thing would go. The mass of 1 mole of ammonia is the sum of the mass numbers. So nitrogen, which is 14 for the mass number, and H, which is 1, but remember we have 3 H atoms, so we'll say 14 plus 3. So the molar mass of ammonia is 17 grams per mole. If we can't get the correct molar mass for atoms or molecules, then our calculation involving the mole will be incorrect. Let's look at the final way of calculating the molar mass, this time using ionic compounds. Here we have an ionic compound, sodium chloride. The mass number of sodium is 23. The mass number of chlorine is 35.5. And so in calculating the molar mass of sodium chloride, we would add the mass numbers of each element. 23 plus 35.5 would give you 58.5 grams per mole. Looking at sodium hydroxide, we would find the molar masses of this compound using the mass numbers of each element. Sodium is 23, oxygen is 16, and hydrogen is 1. And these values you can find in your periodic table. So 1 atom of sodium is 23, plus 1 atom of oxygen, which is 16, plus 1 hydrogen atom, which is 1. And that will give you a sum of 40 grams per mole. Here's a more complicated one in working out the molar mass of this particular compound. This compound is ammonium sulfate. Now, 1 mole of ammonium sulfate would contain the same number of particles as there are in 12 grams of carbon-12. And so we can now work out the molar mass of that compound using the mass numbers. Now, it is nitrogen, which is 14, but we have 2 of them. We have hydrogen, which is 1, but we have 2 4s, 8 of them, plus sulfur, which is 32, and oxygen, which is 16, but we have 4 of them. So we would multiply 2 by the mass number of nitrogen, which is 14, plus 8 times the mass number of hydrogen, which is 1, plus 32, which is the mass number of sulfur, plus 16, which is the mass number of oxygen, that value of 16 times 4, since we have 4 atoms of oxygen. Then we will sum these. So 2 times 14 plus 8 times 1 plus 32 plus 4 times 16 would give us a molar mass of 132 grams per mole. The same method would be done for iron 3 oxide. 2 times the mass of iron, which is 56, plus oxygen, which is 16, but we have 3 atoms there. Sum these values and we'll get a mass of 160 grams per mole. Let us try some other examples involving the calculation of molar masses. Let us try some difficult ones. Aluminum sulfate would be one such compound. If you notice that we have sulfate in bracket. So in order to carry out this calculation, we must know the mass numbers of each element. So we would go to our periodic table and we would look at the mass numbers, if you don't know them by heart. So we would know that aluminum would be 27, but it's 2 of them. So for aluminum, we would have 27 times 2. For sulfur, the mass number is 32. But we have 3 atoms of sulfur. So that would be 32 times 3. For oxygen, the mass number is 16. But we have 3 times 4, which is 12 times the mass of oxygen. So that would be 16 times 12. And then we would add these values and our unit would be grams per mole. 2 times 27 is equal to 54. So we'd have 54 for the mass of aluminum. For sulfur, we would have 3 times 32. And that would give us a mass of 96. For oxygen, we would have a mass of 16 times 12. And that would give us 192. Then we're going to sum these values to get the molar mass of this particular compound. So we would say 54 plus 96 plus 192. And that is equal to 342. So the molar mass of aluminum sulfate is 342 grams per mole. Other examples, you can work on your own by combining any cations with any anions and working out the molar masses using the mass numbers in the periodic table. Let's have a look at working out your units. Remember that moles is equal to mass over molar mass. And we can convert mass into moles times molar mass, or molar mass is equal to mass over moles. So in doing the calculation, let's look at how do I get my unit to be moles if I have the mass and the molar mass of a particular substance. So moles is equal to mass over molar mass. So in doing this particular calculation for the unit of moles, we would have grams over grams per mole. Now this is simply saying that it is grams over grams divided by moles. And another way of writing that is to say grams divided by grams per mole. Now I must change the sign and invert this particular unit. So I'll have grams times mole over grams. And so now grams would cancel grams. So my unit would be moles. If I wanted mass, then I must say mass is equal to moles times molar mass. And we know that MOL is the unit of moles times grams per mole, which is the unit of molar mass. And from that, you'll see that mole would cancel mole. And so your answer in terms of mass would be in grams. So you must work out your units and show your units in the calculation. So if they say find the mass of a certain mole of substance, You cannot give the unit as moles when they want mass. So ensure that the quantity that you're using matches the unit. This concludes our lesson on moles and molar masses.